Here are the notes for day 10. Day 10 is a curve sketching summary. We are going to skip this question here. Maybe we'll come back to it at some point. But the curve sketching summary is a combination of your pre-calc skills and your calc skills. So from pre-calc, you know how to factor a function. If it's a rational function, you will have roots in the numerator. You'll have vertical asymptotes in the denominator. The expanded form is going to help you find horizontal asymptotes. As x gets large, what happens to the fraction? Domain and range, again, vertical and horizontal asymptotes. Intercepts, and then extrema is where the calculus kicks in. Take your first derivative, find the critical values, and then inflection points and concavity, which is the second derivative. So for these problems, I think it's easiest if I walk you through all the algebra steps and then we'll create the graph together. Please pause the video at certain points and copy down the algebra. It's good to have this algebra in your notes so that you can refer to it when you go to do the homework problems. So question says, sketch a graph of this function, labeling intercepts, extrema, points of inflection, and asymptotes. So here's the function. The x-intercept, if you take and solve x cubed equals 9, you need the cube root of 9, which is roughly 2.1. There are no y-intercepts. The vertical asymptote, because this is in the denominator, you're not allowed to have x equal to 0. And the horizontal asymptote, if you look at this, it's going to be slant because the numerator is bigger than the denominator. If you divide everything through by x squared, you wind up with y equals x plus 9 over x. So your slant asymptote is going to look in the long run a lot like y equals x. So let's go ahead and put that stuff on our plot. The x-intercept is at roughly 2.1. I'm going to make every two boxes equal to a unit. So 1, 2, 3. Our x-intercept is 2.1. Our vertical asymptote is that x cannot equal 0. Put a dashed line there. And our horizontal asymptote is actually a slant asymptote, which means in the long run, the plot is going to look like y equals x. Second step is where the calculus starts. Take the derivative. Again, I prefer moving the x squared in the denominator up to the numerator and using the product rule. We get this function here, get a common denominator, x cubed plus 18. If I take and look at critical numbers, x equals 0, and the negative cube root of 18, solving the numerator, we get two critical numbers. So I'm not going to do anything with those critical numbers yet because maybe the second derivative will work out nice and we can do something with that. Second derivative is this function here. If you notice, the denominator is always positive, which means the second derivative is always negative. Since the second derivative is always negative at these critical values, I will have since the second derivative is always negative, we will always have a concave down plot. So when I take and look at the critical numbers, the first is the vertical asymptote, so there is no point there. But the second at negative 2.621, which will be negative 2.6 and roughly negative 4. So I use my calculator to figure out the order pair. Negative 2.6 and negative 4 approximately is where that point is. Now, the interesting part is that because the second derivative is always negative, it's concave down, which means that point needs to be a maximum by the second derivative test. So I know that my function is going to hug this asymptote, hit that maximum point, and then come back down and hug the other vertical asymptote over there. So it's a little bit off the screen, but this point here is a maximum. The other branch, because we know we have a root over here at 2, and because we know that it's concave down everywhere, I can just take and sketch, hug this asymptote, go through that root, and then hug the slant asymptote there. So that's a quick sketch that involved a little bit of algebra that included all the important points. We had intercepts, we had one maximum, point of inflection, there were none because the second derivative is always negative, so it's concave down everywhere. And I have the two asymptotes, the vertical asymptote because of the domain restriction, and the slant asymptote because the numerator was larger than the denominator. So here's a much better looking professionally made graph. Desmos, I typed f of x into there. I typed the slant asymptote y equals x. And then as long as I highlight the f of x, it shows me important points. It turns out that the turning point or the maximum in that area, the local max, is negative 2.621 and negative 3.931. Okay, I would pause the video here, make sure that you have all that algebra down, and you might even want to practice how to take the derivative and the second derivative of that function. So the second example is not a rational function. We have 3 times x minus 1 to the 2/3 and another x minus 1. So the rule is you're going to factor out the lower exponent. So I'm going to take out x minus 1 to the 2/3, and what's left behind is over here. I can set both of those equal to 0, and I can find x-intercepts. The x-intercepts are 1 and 28. Hopefully you can get 28 out of this thing here. It actually grows because you have a cube root, so in order to solve for x, you're going to need to cube both sides. The y-intercept, if you plug in 0 for x, is 4. It's not a rational function, so there are no vertical asymptotes. So let's put that information on the plot. I did a little bit of work ahead of time, and I realized that the x scale needs to be fairly large, but the y scale can remain at 1 box equals 1. So my x-intercepts are at 1 and 28, which is way over here, and my y-intercept is at 4. It's right there. And I don't have a slant asymptote or vertical asymptote, but if we look at the long run behavior like we do with polynomials, the dominant term is this first degree, which is larger than the 2/3 degree. So I think that in the long run, the plot is going to look a lot like, again, y equals negative x, because of the negative in front of this term here. It's going to look, this second part is going to dominate the behavior instead of the first part. So I'm going to put a slant asymptote at y equals negative x, which is going to be steeper than normal because the scale on the x is bigger than the scale on the y. So something along those lines there. Okay, in terms of derivatives, we have the first derivative equal to this. The critical number is 1 and 9. Take the second derivative. We get the second derivative does not exist at x equals 1, and the second derivative is negative at x equals 9. Since the second derivative is negative at x equals 9, we know we have a relative max at 9. Since the second derivative does not exist at x equals 1, we know that the second derivative test fails when I try and look at this critical number x equals 1. So that's kind of important now, so I'm going to say it again. Second derivative is negative when x equals 9. So I know that when x equals 9, I have a horizontal tangent and concave down, which means a maximum. The second derivative does not exist at x equals 1, so I cannot use the second derivative with this critical number here. So I'm going to have to use the first derivative test. So I come down here and say the first derivative at 1 is a critical number. I pick numbers on either side of it, find out that the first derivative is negative and positive when I plug in 0 and 2. Which means the function is decreasing and increasing, which means at 1, I have a local minimum. So putting those two pieces of information on the plot, I know that I have a relative max at 9, 4, right there. I know I have a relative min at 1, 0, which happens to be the intercept. And now I think I have enough to draw the plot. We again have a situation where the second derivative is always negative. I'm going to take the cube root of the denominator, but then raise it to the 4th power. So the denominator is always positive. The numerator is always negative, which means the second derivative is always negative. The graph is concave down everywhere. So I'm going to connect all these points with a concave down function, hug this asymptote, concave down, minimum there, bounce, concave up, and then travel over through the final root, which is right there. And that plot is now finished. So a comment here, it's kind of hard to draw these on an iPad. So this point here should be a maximum. It should be the highest point. So I'm gonna, even if you misdraw, you can maybe write something like, that should be a maximum right there. So here's a much better looking plot using, again, Desmos. Y equals x, concave down everywhere, minimum at 1, 0. Maximum at 9, 4, and another root over here, always concave down. So the final two examples are given a plot of f prime, and you are asked to sketch f and f double prime. So if I take the derivative of what looks like a quadratic, I should get a straight line. So the easier one to start with is f double prime. If f prime is increasing, then I know that the rate of change of f prime is positive. And if f prime is decreasing, I know the rate of change for f prime is negative. So my f double prime is going to go positive, 0, and then negative, and it's going to be 0 at what looks like about 4. So I'm going to take f double prime and draw it in green and have a root there and a positive negative relationship. So again, it makes sense that f prime is what looks like a negative quadratic, which means f double prime would be a straight line with a negative slope. Now to figure out f, I'm going to look at f prime again and say, well, if f prime is negative, then I know that my f function is decreasing. At 0, I have a critical point. If f prime is positive, I know that my f function is increasing. And if f prime is negative, then I know that my f function is decreasing. So if a function goes from decreasing to increasing, I have a minimum. And if a function goes from increasing to decreasing, I have a maximum. So I need to draw a line, and I'll do it in blue, that goes decreasing to a minimum, increasing to a maximum, and then decreasing again. And it looks like the minimum occurs at 0, and then the maximum occurs at somewhere around 9. So I'm going to try and aim for those 2 points. So some sort of a function that decreases to a minimum, increases to a maximum, and then decreases again. And again, because you're going backwards from f prime to f, we don't know exactly how far up or down this blue line is going to be. You could make it lower down here or higher up there. But as long as you have decreasing with a minimum at about that point there, increasing with a maximum somewhere around 9, and decreasing again. Okay, for the last one, we have an f prime graph that is horizontal, straight, and then horizontal again. So I'm going to again start with the second derivative. If I take the derivative of a horizontal line or a constant, I get a 0. If I take the derivative of a horizontal line over here, I get 0. If I take the derivative of this line here, this is a straight line. Figure out its slope. It looks like it's up to right 1, so it looks like the slope of this line is 2. So my f double prime graph is 0, a positive 2, and then back to 0. So in green, the f double prime graph looks like this: 0, up to 2, and then back down to 0. And I'm going to include open endpoints at each of these, because the first derivative does not exist, or the derivative doesn't exist when the derivative from the left and the right are different values. So to figure out the behavior of the f graph, I'm going to look at f prime and determine whether it's positive or negative. F prime is positive, which means f is increasing. F prime is negative, which means f is decreasing. F prime is positive, which means f is increasing. And f prime is positive, which means f is again increasing. So when I switch from increasing to decreasing, I have a maximum. When I switch from decreasing to increasing, I have a minimum. So to finish, let's draw the original f graph in a blue line. The function is increasing up until a max point at about -1. So I'm going to draw some sort of a line that increases till I hit -1. Okay, at that point there, I need to decrease until I hit this point here, because there's a change in the f prime sign from negative to positive. So I'm going to go back to increasing. So I'm going to go up to here. And then the last part, because f prime is flat, I'm going to switch from having a quadratic shape function to a straight line function. So I don't know if you can see that, but this is linear, and this part here is quadratic, and that's because the f function goes from straight line to a horizontal line. So that's your final plot for that. And that ends day 10.